Okay, so 7.5, electric potential due to point charges. We've really been building up our understanding of electric fields and electric potential energy, and this is one of the culminating points. And we're asking in this lesson, if we have a single point charge, a single little item of charge, what is our electric potential going to be from that? What is V going to be from that? And we have a way of calculating that. So to begin with, I'll remind you our electric field, we call this epsilon, and it's equal to kq over r squared. So if we have a point charge, it creates an electric field that has this value at some distance from that point, where r is the distance. So if I want to find the electric potential, V, from a point charge, well, I can use a couple equations that we already have, and we've really built up a lot of equations here. So the first piece is we have delta V is equal to negative epsilon delta D. And so we can use that. I'm going to sort of change from delta V to regular V, and the explanation of how that works is a bit tricky, but you'll just have to trust me here that I'm using this epsilon delta D here to say V is equal to epsilon, which was kq over r squared, but I'm going to multiply it now by delta D, because we have V is epsilon delta D. So kq delta D over r squared. That's our value for V from a point charge. And we can simplify this a bit, because delta D and r are the same thing, and I'll explain that in just a second. So we have kq over r, and this is our V. That's the value of V from a point charge. Now I say delta D and r are equal to each other. R is just the distance we are from our point charge, and delta D is our distance between the point charges. So they are equal to the same thing. All right, and so I'll just put in brackets here, delta D is equal to R. That's how we were able to get that. Okay, so this is an equation we're definitely going to be using. And I'll say something about the sign here. So I'll say that V has the same sign as Q, which is the source charge. And you can also see, I won't write this down, but you can see that as r goes towards infinity, as we get infinitely far from our charge, V is going to drop off to 0. So it's going to go either from positive to 0 if we had a positive source charge, or negative up to 0 if we had a negative source charge. Okay, so that's V, that's electric potential. And we're going to look at one other thing here. We're going to say, what is the electric energy here of two-point charges? So remember, EE is equal to F delta D. E is F delta D. That's something that we have learned a few times, and it's true in electrical energy as well. So E is F delta D, and we have FE. From the very first lesson, FE between two point charges is K Q1 Q2 over R squared. And then we're multiplying that F by delta D, so I'll just add delta D up here. And again, we can simplify that a bit by saying delta D is equal to R. So we get K Q1 Q2 over R. And that is our electric energy between 2 point charges. Again, we used delta D is equal to R. Okay. So one last piece. We have our energy. If I want to find the change in that energy, delta EE, well, this is just equal to the final minus the initial. So we have K Q1 Q2 over RF minus K Q1 Q2 over Ri. Okay, and that is basically our equation. We can simplify that a bit to say it's equal to K Q1 Q2 times 1 over RF minus 1 over Ri. Okay, and so those are all the equations we're working with here. They're all derived from equations we've seen already. Now, so we've got a few problems here. The first one talks about a point charge with a charge of 4 times 10 to the negative 8 coulombs. It's 4 meters due west from a second point charge with negative 1 times 10 to the negative 7 coulombs. First step is we want to calculate the total electric potential due to these charges at a point P 4 meters due north of the first charge. Okay, first step, we want to draw this thing. So we've got our first point charge here. This was 4 times 10 to the negative 8 coulombs. Okay, and that was 4 meters due west of a second object. So there's our second object that we're west of. And this one was negative 1 times 10 to the negative 7. And then we want to test at a point P north of the first charge, 4 meters north. So this is 4 meters, that was 4 meters, and we're going to need to find that distance at some point. Okay, so this is our situation. This was point P. And what we want to do is figure out the total electric potential. Well, because electric potential, it's just a scalar, it's not a vector. So we can actually say that Vt is equal to V1 plus V2, and we're not going to have to do any vector math. It's just the scalar quantities added together. So we can get V1. So this is the potential from the first charge. It's K Q1 over R1P. So the distance between object 1 and point P. And we can just fill in our numbers. Remember, K is a constant, 8.99 times 10 to the 9. We've got our Q1, 4.00 times 10 to the negative 8. And divide by our radius, which was 4 meters. And this gives us 8.99 times 10 to the 1 joules per coulomb. That's V1. We do the same thing for V2. V2 is equal to K Q2 over R2P, the distance between object 2 and point P. Now for this we're actually going to have to figure out what that distance is. So we can say here R2P is equal to the square root of, well, we've got a triangle here, it's 4 squared plus 4 squared. This will get us our value. So R2P is equal to 5.6569 meters. Okay, so we can fill in our numbers now. We've got 8.99 times 10 to the 9. And we have our new charge, negative 1.00 times 10 to the negative 7. Divide that all by our new distance here. It's 5.6569. And that gives us negative 1.5892 joules per coulomb. Excellent. So then we can get our total voltage, our total electric potential, and that is equal to V1 plus V2. So we've got here 8.99 times 10 to the 1, 10 to the 1, minus 1.58, I'll fix that in a second, 8.99 times 10 to the 1, minus 1.5892. And this is equal to, okay, I had a bit of an interruption there actually, but we're back to this, and I wanted to point out that there was a mistake. This negative 1.5892, this was times 10 to the 2 here, times 10 to the 2. And so that means that this guy down here, we have times 10 to the 2, and that's going to change our answer quite a bit. So now we get a negative number. Our answer is negative 69.02 joules per coulomb. Okay, so that is our final total electric potential at point P. Good. Now, next piece here, we want to calculate the work required to bring a third point charge with a charge of 2.0 times 10 to the negative 9 coulombs from infinity to point P. And now, so you're going to see this a bit, this idea of bringing something from infinity. And especially once you get into university, that's often going to be the idea as well. The idea is that at a distance of infinity, we have a potential basically of 0. We have a total potential of 0, because the further away you get, well, it decreases with r squared, so infinity, you have a potential of 0. So when you're bringing something in from infinity, the total work, it's going to be the sort of the energy, the change in energy that's required there. So this is what we have here. Work is equal to the negative change in energy. Right, because this is if we're increasing the energy of the system, we're having to do work on it. So, so we've got our negative change in energy. This is negative Q delta V. That's from one of our many equations. And our delta V, so I can say Q, the V of infinity, minus our total V at point P. Okay, and our V at infinity is going to be, so Q, our V at infinity is just 0 minus our total V. So we get negative Q V total. That's our work. That's the work required. So we can give this a try here. We get the work is equal to negative, and then we have Q was 2.0 times 10 to the 9. 10 to the negative 9. And our VT was from above 69.02. This gives us a total work of 1.4 times 10 to the negative 7 joules. That's how much energy, how much work it takes to bring that particle in. And there we go. That's how we do those sorts of problems. The next page here, we have a point charge Q1 with charge 2 times 10 to the negative 6 coulombs is initially at rest at a distance of 0.25 meters from a second charge, Q2, with a charge of 8 times 10 to the negative 6, and mass 4 times 10 to the negative 9. Okay, charge Q1 remains fixed at the origin, whereas Q2 travels to the right upon release. Well, that makes sense. They're both positive charges. They're going to push away from each other, but Q1, it doesn't move. Determine the speed of charge Q2 when it reaches a distance of 0.5 meters from Q1. So they start at 0.25, they go to 0.5. I'm going to draw our situation here. So we have Q1. This is my Q1 here. And this here has a distance. So here's Q2. This has a distance of 0.25 meters to begin with. And it has an initial speed of 0. And it ends up traveling in this direction to, I'll draw sort of the circle here. This is its final position, where we have another 0.25, or we can say this total distance here is 0.5 meters. Okay, so that means that this new distance here is 0.25. All right, and we have this guy, and we want to find the final velocity, the final speed. This is what we're looking for. So how do we do this? Well, we are converting, we're converting our electric energy into kinetic energy. So we have EE is being converted to EK. Another way we can say this is that delta EK, the change in kinetic energy, well, it's going to be positive, is equal to the negative change in electric energy, because as one goes up, the other one goes down. So we've got this positive-negative relationship. Okay, so let's see. We have 0 initial kinetic energy, so if I look at my kinetic energy here, I can say EKF is going to equal to the initial electrical energy minus the final electrical energy. So that tells us how much electrical energy we're giving up to kinetic. And then I can say 1/2 mv squared. And I can fill in this here. We have K Q1 Q2 over R1 minus K Q1 Q2 over R2. And I can simplify that a bit. I can say this is equal to K Q1 Q2 times 1 over okay, well, yeah, let's just do this here. 1 over R1 minus 1 over R2. Okay. So we do have some information here. R1 and R2, we know that, well, we have those numbers here. So I can fill that in. Let's see. So this is K Q1 Q2, and I'm just going to do 1 over R1 minus 1 over R2. So we get 1 over 0.25 minus 1 over 0.5. So we have k q1 q2 times, let's see, 0.25, 1 over 0.25, so that's 4, minus 1 over 0.5, so that's 4 minus 2, we get 2. Hopefully that's clear enough for you, that little bit there. Okay, so we've got some information now. I can say 1/2 mv squared is equal to all this. So if I want to solve for v, I can say v is equal to the square root of, well, I'm going to multiply the other side by 2, and it already had a 2 on there, so I get 4 k q1 q2 over m. And I can put in some numbers now. Good. So let's get some numbers here. Oh, and I'm sorry, I left off. No, this is good. Okay, great. So we've got the square root now of 4 times k, which is our 8.99 constant. 8.99 times 10 to the 9 times q1, which is 2 times 10 to the negative 6, and q2, which is 8 times 10 to the negative 6. Square root of all this, divide that by our mass, which is 4 times 10 to the negative 9. And let's see, if you put that all into the calculator, you should get a value of 1.2 times 10 to the 4 meters per second. Okay, so there we go. Our last problem is a head-on collision. Well, collision is in quotes because we're not dealing with conservation of momentum or anything here. But the idea is that we have two things that are going to collide with each other. So we have two particles, a proton with charge 1.6 times 10 to the negative 19, and that mass. And we have an alpha particle with, which is a helium-4 nucleus, with this charge and this mass. They're separated by an extremely large distance. They approach each other along a straight line with initial speeds of 3 times 10 to the 6 meters per second each. And we want to calculate the separation between the particles when they're closest to each other. Alright, so again, this is a conservation of energy problem. We're converting all of the kinetic energy of both of these guys into electric potential energy. So we can say here the change in electric potential is equal to the negative change in kinetic energy. Similar to the last problem. And let's see, this time we start with all kinetic, no electric, and we end with all electric, no kinetic. So I can say now the electric final is equal to the kinetic initial. I'm converting all the kinetic energy in the start to electric energy at the end. So now I have some equations. I have k q1 q2 over r is equal to 1/2. And now they both have some speed. They have the same speed, so I can say m1 plus m2 times their v squared. And that's going to be my conservation of energy. So to clean this up a bit, I'll move the r over, and I'll move the 1/2 over to the other side. So we've got 2k q1 q2 is equal to, oops, sorry, r m1 plus m2 v squared. Good. Now what we want to do is we want to find how far apart are they. So we want to find this radius. So we can rearrange here. R is equal to 2k q1 q2 over m1 plus m2 v squared. There we go. And now it's just a matter of plugging in some numbers. So we have 2 times 8.99 times 10 to the 9 times 1.6 times 10 to the negative 19 times 3.2 times 10 to the negative 19 all over, we've got the mass of one and the mass of the other, so we have 6.64 times 10 to the negative 27 plus the second mass, which is, oh, that was the second mass, I'm sorry. The first mass is 1.67 times 10 to the negative 27. And all of that times our v squared, which is 3 times 10 to the 6 squared. All right, plug all those numbers in, and we should get a grand total here of 1.23 times 10 to the negative 14 meters. And there we go. It's our final answer. Those are the sorts of problems we're dealing with. We have one last lesson in this chapter, and it should be a shorter one. I hope you enjoy.